Welcome to homework.
31.18. So we have an oscillating LC circuit, and the amplitudes of current and voltage are 7.5 milliamps and 250 millivolts respectively, and the capacitor has a value of 220 nanofarads. So we want to find some things, one of which is the period of the oscillation, the maximum energies stored in the inductor and the capacitor, the maximum rate of change of current, and the maximum rate of change of the inductor's energy. So we know from the sort of general Ohm's law for a capacitor that the amplitude of the voltage equals the amplitude of the current times the reactance, in this case of the capacitor. So omega is going to be I over CV Now the period is 2 pi over omega. And so then just evaluating that, we find that the period is 46.1 microseconds. So now the maximum energy the capacitor stores in its electric field is 1/2 CV squared. And so if this is the amplitude, then that's the maximum value it will take. And so this is 6.88 times 10 to the negative 9th joules. So now the maximum energy that the inductor stores, in principle, is L I squared over 2, which is a problem because we don't know what L is. We know what C is and we know the frequency, so we could figure it out. But also we don't have to because of the conservation of energy. And we know that it goes back and forth between all being in the capacitor and all being in the inductor, that its maximum has to be the same. And in fact, this is the total energy in the system. So start a new one. So now we want to find the IDT, or the maximum dIDT. So we know that the voltage across the inductor is equal to L, the amplitude of that voltage, is going to be dIDT maximum. We know that from the the inductance has to be CV squared over I squared, which we can find from what we use to find the period in part A. And so then putting that in and then solving for dIDT max, we get that so this will be V over L. So this is V over CV squared over I squared. this is I squared over CV. And so this is 1.02 times 10 to the third amperes per second. Then in a similar manner, we can write down the expression for the energy stored in the inductor, L, the function of time I squared. So we take the derivative of this, and so we have L I squared omega if you wanted the time-dependent version, there would be a sine of 2 omega t, but we just want the maximum, and we know that the maximum of sine of anything is 1. And so we know we can substitute in what we know for L and omega. We end up getting 1/2 IV, which first of all makes some amount of sense because we know that current times voltage is power, and here's a factor of 1/2 that makes sense with it being the phase difference or something along those lines. We at least know it'll have the right units. So this will be 0.938 milliwatts.